Hi, it is part 3 of section 4.1, surrogate minimization or unifying principle. Here, we'll try to derive the gradient descent method by using surrogate minimization. The technique can be used for the derivation of other methods, such as Newton method and its variants. Here, we'll try to consider mathematical background of surrogate minimization. The key idea in the technique is given as follows. Okay, let's xn be the current iterate. Then around the xn, we try to construct approximating function qn, and now by minimizing the approximating function, we try to get new iterates. So xn plus 1 is minimizer of local the approximating function qn, and here the qn is called surrogate function or math function. The surrogate function should be easy to optimize and flexible enough to approximate a wide range of functions. Let's see the detail of the technique for gradient descent method. And xn is current iterate. Then we consider the quadratic surrogate function in this form. And cn is constant, and gn is a vector, and that is the quadratic term, and with the scaling. Now, for this surrogate function, the requirement is that this should be coincide with the original function in its value and first derivative, which means gradient. So here now, qn at xn and f of xn is same, means that once x is xn, then this will disappear, so that cn must be f of xn. Now, after taking gradient of qn and we put xn, then this will disappear and this constant will disappear. Only remaining part is gn, so the gn must be gradient of f at xn. So we can rewrite the surrogate function in this form. So qn of x, so that is quadratic approximating function around xn, and that is f over xn and gradient of f at xn dot x minus xn, and this is a second order term. Now, this is simple second order term, so that quite easy to optimize, and you can find the minimizer quite easily. Here, easy to optimize and flexible enough to approximate a wide range of functions. Okay, so here, if you try to optimize qnx, then now take a gradient and equal 0 and solve for x to have now xn plus 1. So if you take a gradient, then this will disappear, and then that one will be here. Okay, this term is the same as, okay, squared. Norm squared is same as, now, in fact, this is the same as x minus xn, now, dot x minus xn. So if you take derivative, then the gradient, then twice of x minus xn. So here, gradient of qn will be same as now gradient of f xn. Here derivative will make this part disappear, and then now that one will be plus here 1 over gamma, and now x minus xn. If you put 0 and solve for x, then you can get that one. So the solution minimizer is now new iterate. That's the idea of using surrogate approximation. And now, along with different form of surrogate function, and you can derive some other algorithms. But for gradient descent method, the quadratic term is just the simplest one, and only requirement is now the same value for fn is gradient. Okay, that is a subject in the third part, and also we'll go here another subject is quite important, multiple local minima problem. Although you can choose the step size smartly, and if you reformulate your algorithm much better way, there is no guarantee for your algorithm to converge to the desired solution. The desired solution is global minimum. But if the objective function is non-convex, or there are some multiple local minima, then your algorithm will converge to a local minimum. But you can overcome the problem for some cases by using so-called Gaussian homotopy continuation. And here, the method begins by trying to find a convex approximation of the optimization problem. And so that is called Gaussian smoothing. Okay, let's see the figure here. Now, this is the original objective function. Then initial value must be really good. If not, for example, your initial value is around here, then it'll approach or converge to this point, which is a local minimum. However, it's not the desired solution. So rather than solving this one, you may try smooth the objective function, so that, for example, you can make such a smooth one, but its minimizer is not the same as the minimizer of original objective function. However, you may start with this one, and now less smoothed curve can be used by using this one. Now start with here now for less smoothed objective function can locate the minimum here. And again, one more time, less smoothed objective function will be used to begin with here and locate this minimum. And eventually, by using the original objective function, you can find the global minimum. So that is now idea of the Gaussian smoothing or Gaussian homotopy continuation. It is a kind of a frequency continuation. Now, this Gaussian smoothing is along with weighted averaging. So that's the reason it's called Gaussian smoothing. Here, the values for each point, the values will be averaged by using surrounding values. And if you try to use more values, and then you can get smoother object function. And let's then less smooth objective function. So by using many stages of smoothing objective functions, and from the smoothest one, you are trying to minimize, and by using the minimizer, now here we use it as an initial value and minimize, and now the value will be used for next stage as the initial value, and then minimize the objective function and so on, so that you can get here good the good convergence anyway. So that is called an optimization problem. But this one is quite necessary when you are dealing with multiple local minima problem. It's very hard. Now, one more thing to overcome multiple local minima problem is related with stochastic gradient descent method. When you are using only a part of data, small number of data points, or small number of components from the objective function, then the objective function will become smoother, so that the multiple local minima problem will not be so severe, so that you can overcome this issue. And so that's the reason in modern machine learning society, the stochastic or mini-batch algorithms are so popular. And most cases, it is overcoming multiple local minima problem. Of course, one solution is not solving the issue. You may try to solve the problem many times with random access of data, or random access of random organization of the objective function. Then you can get various results. And if you do many times, then here you can compare the best one and the result to get the best one. With that strategy, in many cases, you can overcome the multiple local minima problem. Okay, that is at the end of section. Thank you.